Hello, today we're going to talk about empirical formulas and how to find them in a variety of different ways. All right, so first, just a definition of an empirical formula versus a molecular formula. So you can think of the molecular formula as the whole molecule. So we know that when we form molecules, we're forming covalent bonds, right? And so there's a specific number of each kind of atom in our molecule, and that's represented by the molecular formula. The empirical formula is kind of like the reduced formula, all right? So just like in math, if you were to reduce a fraction from like 2/4 to 1/2, that's what we're doing with an empirical formula. So for example, in part A here, we have C2H2, all right? So all of the subscripts here can be divided by 2. So if we wanted the lowest whole number ratio of carbon to hydrogen, that would be CH, all right? For this one here, we have a 5, a 10, and a 5. So the lowest whole number ratio for this one would be if we divided all of those numbers by 5, because that's the biggest number that can go into each of them. So if we did that, we'd have 1 carbon, 2 hydrogens, and 1 oxygen. So our empirical formula would be CH2O, all right? And then the last one we have here is NH3. All right, in this case, we only have 1 nitrogen, so there's no way to reduce this anymore, all right? So when you only have one of a particular element, you can't reduce it, so the empirical formula is just the same. Doesn't mean it doesn't have an empirical formula, it just means that we've already reached the most reduced form. Right. So we can, in addition to finding them from the molecular formula like we just did, we can also use experimental data to determine how many or what the empirical formula is going to be. So I've listed the steps here for how we will do that. The first is to calculate the number of moles of each element, right? So in this compound, we have an iron compound, and it has iron in it and it has chlorine in it. So those are our 2 elements, and we need to figure out how many moles of each of them we have, all right? We can't get a ratio from grams, right? This would be like if I have a pound of cheese and a pound of ham, I can't tell how many sandwiches I can make because I don't know how many slices of each are in a pound, right? So we need to get to a number first, right? So the first thing we'll do is the 6.87 grams of iron. This is the molar mass of iron. These are just gram to mole conversions like we were doing in the previous lesson, right? And so that is 0.123 moles of iron. And then the second one would be the 13.1 grams of chlorine. Again, use the molar mass from your periodic table and get 0.370 moles. All right, so you can look at this and maybe say, okay, that's like about 1 to 3, but we're actually going to mathematically figure out the ratio by dividing by the lowest number of moles. So step 2 is divide by the smallest number of moles. In this particular problem, we only have 2 elements, but you could have more than 2, and you would still divide by the smallest one. So we'll take both of these number of moles, divide by 0.123, because that is our smaller number. Okay, so 0.123 divided by 0.123 is just going to be 1, all right? And 0.370 divided by 0.123 gives us 3, okay? It will not always work out to be a perfect whole number, okay? In your notes, there is a table that tells you what to multiply by if the number is not exactly a whole number, okay? So you can round if it's like 0.9 something, all right? Or like 0.01 or something like that. But if it's like, you know, if we'd gotten 2.5 here, that's not close to a whole number. But if we multiply both numbers by 2, then we'll have whole numbers. So usually I would only have you multiply by 2 or by 3. There are obviously some examples where the ratio is going to be higher than that. But for our class, you can expect that one of those would work. All right, and we'll do some examples like that in class as well. All right, so here we have the ratio is 1 to 3, right? So then our formula is just going to be FeCl3. It's just that ratio, right? And again, this is an empirical formula. Later in the lesson, we'll talk about how you would get a molecular formula if you were given this kind of data. Okay, so molecular formulas. Molecular formulas, like I said, is just before we reduce it, basically. So now we're going to go the other direction, basically. So if we had an empirical formula that was CH2O, which of these could possibly be the molecular formula? We don't have enough information to know which one it is, all right? If the empirical formula is CH2O, then CH2O could be the molecular formula. It's possible that it's already reduced, right? Remember that we had that with NH3 earlier, okay? If this was our molecular formula, we have 2 carbons, 4 hydrogens, and just 1 oxygen, so that one can't be reduced anymore, so it can't be, that can't be the molecular formula, so that one will not work. All right, this one we have 2 to 4 to 2. If we reduce that, the ratio would be 1 to 2 to 1, which is the same as what we have up here. So that one could possibly be our molecular formula. Up here, we have the same problem we did before. There's only 1 oxygen, so we can't reduce this one. Right here, it's 3 to 3 to 3. That's 1 to 1 to 1. That is not the same as the ratio that we have here. And here we have 5 to 10 to 5. So all of those are divisible by 5, so we could get 1 to 2 to 1. And that one could also potentially be a molecular formula. Okay, so let's talk about how we would get it from data, right? So here we have some options, but if we had some data, we could probably figure out which one it is. All right, so if our molecular formula, so let's talk about empirical mass versus molecular mass. I'm getting ahead of myself. So if the molecular formula for ribose is C5H10O5, then the empirical formula would be CH2O, right? So that's one we just looked at in the previous slide. All right, so we have a molar mass that we can calculate for the whole molecule, and we could also calculate an empirical mass. So let's do each of those. So the molar mass is just like we've been doing, 5 times the mass of carbon plus 10 times the mass of hydrogen plus 5 times the mass of oxygen. Okay, so that would be our molar mass for ribose. Our empirical mass, we could do 2 different ways based on the information that we have here. We could just do carbon plus 2 hydrogens plus oxygen, right? Because we already have our empirical formula, right? But because this is 5 times the empirical formula, we could also take the molar mass that we just calculated and divide it by 5, and that would also give us the empirical mass. All right, so now let's do a problem. If we have an empirical formula for vitamin C is C3H4O3, all right, and we know the molar mass is 176.12 grams, how could we get the molecular formula? Okay, so we know that the actual formula for vitamin C has to be some multiple of this. Let's figure out what this mass is first. That's our empirical mass. So our empirical mass is going to be 3 times the mass of carbon, plus 4 times the mass of hydrogen, plus 3 times the mass of oxygen. So that's 88.062 grams per mole. Right? Our molar mass for this compound is 176. So this isn't the molecular formula, right? Because it's not, the masses are not the same. But we know that the molecular formula has to be some whole number times the empirical formula, which means that the molecular mass must be a whole number times the empirical mass. So we know our molecular mass is 176.12. All right, we know our empirical mass is 88.062. So if we solve for that whole number, we'll find out that there must be 2 of those empirical formulas in the molecular formula. All right, so now we just take all of the subscripts in our empirical formula and multiply them by 2. All right, and we'll get in a molecular formula of C6H8O6.